Hey, hi everyone. So from the last video, we have taken this definition to prove that this definition here actually did result in the electric potential energy, and at the same time we know that because there's two types of work done, so these two types of either the work done by external force or the work done by electric force, if you can word them properly, in this case if it's work done by electric force, you need to add on a negative. You word them properly, they will be representing the definition of electric potential energy. Okay, so electric potential energy can be defined based on work done, and if you understand the relationship based on the earlier videos, then you're able to word the definition properly to represent the electric potential energy. And you use this definition over here and you flip it to determine the equation for electric potential energy over here. So we know that it's just the work done is just the area under the force distance graph. So once we do the integration, we arrive at this equation over here. So this equation here represents the electric potential energy in between a pair of charge over here. Okay, so in between this pair of charge, store an amount of electric potential energy, and how much is it can be determined by using this equation over here. Okay, then afterwards we look at situation where you have more than two charges. For example, let's say if you have three charges, then the question can ask you electric potential energy associated with a certain charge. They only need to add up EPE related to that specific charge. Or if they ask for the total electric potential energy or the electric potential energy of the system, they need to add up all the springs here in order to obtain the total electric potential energy. So I'm going to sort of wrap up my discussion on electric potential energy. Now I'm going to discuss electric potential actually. Okay, so it's still in section 2, but right now I'm going to talk about electric potential. Okay. So electric potential is the topic for this particular video, but I'm not going to discuss electric potential directly by giving you all the definitions and stuff. Okay, actually in my perspective is electric potential is actually very similar to electric field. Okay, the purpose of learning electric field is the same as the purpose of learning electric potential. Okay, it's because you have charges that are not touching each other. If they're not touching each other, how do they interact with each other, right? So you need some kind of medium in order for them to interact. So electric field is its existence is used to explain why there's electric force in between charges. Okay, so electric potential, it exists to explain why there's electric potential energy when you put the charge at a certain position. Okay, so I'm going to draw parallel between these two concepts, the electric field and the electric potential, so they can see how you are going to think of electric potential. Okay, so over here I'm going to compare between two things, right? So let's write down. The first thing is I'm going to write about electric field first. So this is electric field. Okay, I'm going to compare it to electric field. So electric field, the symbol is E. Then the unit for electric field, it's Newton per Coulomb. Okay, so this is what we learned in section 1 when we learned about electric field and electric force. So I'm going to draw parallel between these two things. So I'm going to compare it, okay, in between this and also electric potential. Okay, so electric potential is not electric potential energy, definitely. Okay, electric potential energy is the energy, but electric potential is a slightly different thing. Okay, the symbol for electric potential is V, and the unit is just volt. Okay, so these are the two things that I'm going to compare between. Okay, so we learned from the previous section that electric field is actually a vector field. Produced due to the presence of one or more charge. Okay, not going to explain the whole thing again in detail. I'm going to just roughly go over it because, well, we learned about it in the previous section already. So let's say today I have a charge over here, and this charge here I'm going to name it as Q1. Okay, and now because of the existence of this charge, okay, we have this charge being placed in this region over here, and because of the existence or the presence of this charge, the surrounding here will have a vector field produced by this Q1. Okay, you can think of it like the aura of a person standing in a room, then the aura of this person permeates through the room. Or if he or she is wearing a perfume, okay, the scent of the perfume permeates through the room. Okay, you can think of it in many ways, okay, but it's a kind of field. Okay, in this case, this electric field exists, okay, or this electric field is produced by this Q1 and it covers the whole region. The whole region over here has an electric field that is produced by Q1. Okay, so let's say if I am interested to know, let's say, the electric field at this position. Okay, so at this position here, there will be electric field produced by Q1. So Q1 will be responsible for producing the electric field at this position. So if you want to determine the equation and determine the electric field at that particular position, okay, produce. If you want to know the electric field at that particular position and it's produced by a point charge, you can use this equation. E is equals to KQ over R square. Okay, this equation here can only be used if it's a point charge. Okay, but I want to make some note in which this Q here is the charge that produces the electric field. Okay, in our situation here, because we have only one charge Q1 over here, the presence of this Q1 causes an electric field being produced around Q1. And since this is a point that is around Q1, that's why this point over here has an electric field that is produced by Q1. So this is the only charge over here. So if you want to know the electric field at this point, you can just put in Q1 into here because Q1 is the charge that is producing the electric field over here. So put Q1 inside here. Then we find the distance over here. We submit everything. We can find the strength of the electric field at this position. Okay. So to add on some context, this is the distance that we have right now. This is the distance R. Okay, so this is how we determine the magnitude right now. I should probably move a bit. Misplace stuff. This is the magnitude. Okay, right now I'm talking about the magnitude, so-called electric field strength. Okay, use. So right now I'm talking about the magnitude. Okay, if I talk about direction, the direction, I mean, it's not that complicated as well. If it's produced, if the electric field is produced by a positive charge, then what we can know is that the electric field will point away from the positive charge. Okay, but if today the electric field is produced by a negative charge, okay, then what happens is the electric field that is produced by the negative charge here will be pointing towards the negative charge that produced the electric field. Okay, so this is what we should know regarding the electric field being produced by this charge at this point over here. To find the strength, we use this equation, substitute the charge that produced the electric field. find the distance between the charge that produces electric field and the point which you are interested in. That distance is r. So you substitute everything, you get the magnitude of electric field. So if you want to know whether electric field is pointing which direction, you see what charge is producing it. If it's a positive charge that is producing it, the electric field is going to point away from the positive charge. So since this is a positive charge Q1, we know the electric field produced by this Q1 over here, okay, is going to point in this direction. Okay, I'm going to call this electric field at, let's call this point X maybe. Electric field at point X, not a nice place to place the X. Electric field produced at point X. This one is called point Y lah. Okay, so this is the electric field produced at point X by Q1. Okay, there's many ways to write this. It might get confusing because from time to time, I mean, different lecturers, they come to discussion, they think of different convention, whether they want to use by what charge at where or at where by what charge. Okay, so for now I'm using at where by what charge, but in certain videos I'm using by what at where. Okay, you have to listen to the explanation. I'll state it clearly whether it's by what on what or on what by what, or by what at where or at where by what. In this case, it's at where by what. So because it's at where by what, this will be at point X and it's produced by charge 1. Okay, electric field produced at X by Q1. Okay, so this is how I determine it. Okay, right now I'm going to move on to talk about interact. Okay, so what is interact? Okay, so we know that charges, they produce an electric field around it. So what if there's a charge being placed at the place where there is electric field? Okay, let's say I place a negative charge over here. And this negative charge is Q2. So because Q2 is being placed over here at this position, what happens is Q2 will be interacting with the electric field that is at this particular position. Q2 is standing over here, so it will be interacting with the electric field at this position. And for this situation, the electric field at this position is produced by Q1 as mentioned over here. Who is going to interact with the electric field at this position? It is Q2 that will be interacting with the electric field at this position. Okay, maybe let me tidy it up a little. So over here at this position X, there's electric field produced by Q1, and because Q2 is standing at this position, you'll be interacting with the electric field at X, and the electric field at X is produced by Q1. Okay, so because it's interacting with the electric field, as a response of this interaction, Q2 will be experiencing an electric force. Q2 interacts with the electric field. As a result, Q2 experiences a force. So we need to find an equation that relates between the electric field that is interacting with and the response, which is the electric force experienced by the charge. So this there's an equation that can relate them together. So if you want to study the magnitude of this interaction, then we can use the equation in which the electric field strength is equals to the force experienced by the charge per unit charge. Okay, so this equation here, we need to be very careful, in which you need to know that the Q over here is a Q that is interacting with the electric field. Charge that interacts with electric field. Okay, and since for this particular situation up here, Q2 is the one interacting, so we should substitute the magnitude of charge Q2 inside here. Okay, this E here is the electric field that Q2 is interacting, so which is the electric field at point position X, and this F here is the force experienced by Q2. So the force experienced by Q2, if we use the convention on what by what? This will be on 2 by 1. Okay, this is the force experienced by on charge 2 and is exerted by charge 1. Okay, the electric field over here is the electric field at X and it's produced by charge 1. Okay, I hope it's not confusing over here, but I'm going to keep it general because different situation they label charge differently, right? So I'm just keep it as E and F. Okay, but for this particular situation, technically you should write this force here as force on 2 by 1, F21. This one is electric field at X by Q1, so X1. Okay, so this is how you should label them. Then the charge over here is charge 2 because charge 2 is interacting over here. I'm talking specifically at position X. I'm not talking about position Y yet. Okay, so this is the equation that you use to relate the force and the electric field. Then for the direction, okay, we need to know that if it's a positive charge that is interacting with the electric field, if it's a positive charge interacting with the electric field, then what we need to know is that the force experienced by the charge and the electric field that it is interacting with is in the same direction. Okay, however, if it's a negative charge that is interacting with the electric field, which is the case up there, it's a negative charge interacting with the electric field, then what we should know is that the electric force experienced by the charge and the electric field that is interacting with is in the opposite direction. Okay, so if you look up here back to this situation at position X, we know that the charge that is interacting here is Q2 and Q2 is a negative charge. So the electric force experienced by Q2 will be opposite direction to the electric field that is interacting with. The electric field that is interacting with is pointing to the right, therefore the electric force that is experienced by Q2 will be pointing to the left. The force experience on 2 and is exerted by 1. Okay, so this is how you should label it. Okay, so this is how you should understand produce and interact. The existence of a charge produce an electric field around it, and if another charge happens to step on that position, they interact with the electric field at that position, then as a result you experience a force. Okay, you can use the whole explanation here to study the position QY, the position at Y actually. At position Y, there is electric field that is produced by Q2. Because the presence of Q2 here will produce an electric field around Q2, right? So position Y happens to be around Q2. So position Y will have an electric field that is produced by Q2. Okay, let's write it down. It has an electric field that is produced by Q2. Okay, but because Q1 happens to step on position Y, so Q1 will be interacting with the electric field at position Y. Okay, it's like if I have a nose, if I stand at this position, I will smell the scent over here, right? So I'll be interacting with the electric field at the position that I'm standing in. Okay, so I'll be standing here, so that means I'll be interacting. So that means the charge is interacting with the electric field at position Y is Q1. Okay, so Q1 here, because it's standing at Y, you interact with the electric field at Y. The electric field at Y is produced by Q2 actually. Okay, so if you study the direction, the electric field at Y is produced by Q2. So Q2 is a negative charge. So if the electric field is produced by a negative charge, the electric field will point towards a negative charge. So the electric field at this position will point towards the negative charge. So you have to point to the right. If you're pointing to the left, you're pointing away from Q2, right? So if you're pointing to the right, you're pointing towards Q2. So that means there's an electric field that is pointing to this direction. and this is the electric field that is produced at position Y, but is produced by charge 2. Okay, so EY2 is produced at position Y by charge 2, at Y by Q2, at Y by Q2. Okay, so Q1 is interacting with this electric field. Q1 is interacting with it, and because Q1 is a positive charge, so positive charge interacting with the electric field, the force and the electric field should be in the same direction. So Q1 will be experiencing a force in the same direction as the electric field. Therefore, you can see that the electric force will be pointing in the same direction. So this one we call it as force experienced by 1 and is exerted on 2. Okay, you can see that the force and the electric field are in the same direction, and if you check the force, these forces are pointing towards each other, so it's an attractive force which match with the situation where you have a pair of unlike charges or opposite charges. Okay, so this is a quite in detail explanation. I didn't intend to go that deep, but I think this is a quite a complete comprehensive discussion of the magnitude and direction of the electric field produced by a certain charge or interacted by a certain charge. Okay, so I'm going to draw parallel of what we have learned here about electric field in section 1. I'm going to draw parallel to it to electric potential. Okay, because electric potential is actually a similar concept, just that electric potential is not a vector field. Electric potential is a scalar field. Okay, so this is the definition. It is actually a scalar field produced due to the presence. Okay, I think you know that the rest is the same. It's produced due to the presence of one or more charge bodies. Okay, so the same idea. Okay, just now you say because there's a presence of one single charge, the region around it is filled with an electric field or an aura or a perfume scent, right? This is a similar idea. The presence of a charge produces an electric potential around the region. Okay, but this electric potential, how is it different from electric field? Electric field, there's a direction to it. But when we talk about electric potential, there is no direction to it. It's just a feel, just like smell, a scent, or an aura. This one has no particular direction to it. Okay, before this, when we talk about electric field, the electric field has direction. It means by that aura has a direction, but this one, the aura does not have a direction. Okay, so I'm going to use the same scenario as the left. So there will be position Y and there will be position X, just like just now. Okay, so let's start with having Q1 being placed at Y. Okay, so there's Q1 being placed at Y. Okay, so because Q1 is being placed at Y, it resulted in position X to have an electric potential that is produced by Q1. Okay, so if you want to study the electric potential produced by Q1, how strong is it? You will use a very similar formula. Okay, the distance here is R. Okay, so if you want to find how strong is the electric potential at this position, and you happen to know that this position, the electric potential is produced by Q1, so you can determine the strength of the electric potential by using this equation. V is equals to KQ over R. Okay, later I will discuss with you how does this equation sort of come from. But for now, I just know that this is KQ over R. Okay, then as usual, this Q over here, I should make some note in which this is the charge that produces the electric potential. Okay, so this equation, I want you to take note that similar like the previous video, there's no modulus here. Okay, so sub in the sign of the charge. Okay, so the sign of the charge, you need to put it into the equation as well. Previously, when we talk about electric field, we modulus out all the charge, right? So we don't need to put in the sign when we substitute in the electric field. But right now we're talking about electric potential, so we need to substitute in the sign of the charge as well. Okay, so this is the equation. Now, if you think about direction, okay, I just want to clarify that because this is a scalar field, right? Scalar field means by there's no direction involved. Okay, we are not going to talk about direction. Okay, so right now, continuing on a similar scenario, we know that position X it's not that there's nothing like position X. At position X, there's actually Q2 that exists over there. Okay, so we're going to place Q2 at the position. Okay, so what happened is the presence of Q2 at position X will cause Q2 to interact with the electric potential produced by Q1. Okay, Q2 exists at position X, so Q2 will interact with the electric potential at position X. And at position X, the electric potential is produced by Q1. So Q2 will be interacting with the electric potential produced by Q1. Okay, this position, there's an electric potential. Q2 is interacting with it. And the electric potential that is interacting with is actually produced by Q1. So to study the interaction, we need to understand what's the response of the interaction. Okay, if you think about it, just now, the result of the interaction is the charge experience of force. But right now, we are talking about scalar, so there's no such thing as direction over here. So what's the result of it? Okay, the idea is if Q2 interact with the electric potential at position X, what happens is Q2 together with Q1 will share an electric potential energy in between them. Okay, the existence of Q2 at position X causes Q2 to interact with the electric potential over here. Okay, so Q2 is interacting with the electric potential over here. As a result, Q2 will possess an electric potential energy that we have just learned from the previous video. The result of the interaction is it possesses an energy. It becomes excited, it becomes energetic, it possesses some amount of energy, which is the electric potential energy. How much is the electric potential energy? Well, you actually know about it. You know that if there's a pair of charge, we can draw a spring in between them, right? And you know that this spring in between them, there will be potential energy, electric potential energy, which can be calculated by K Q1 Q2 over R. Okay, this is the energy that will be possessed by Q2 and shared with Q1 because of the existence of Q2 at X. Q2 stands at X. Q2 interacts with the electric potential at X. The electric potential at X is produced by Q1. Therefore, Q1 and Q2 will share an electric potential energy, U. Okay, so the response here is the potential energy. Knowing that, we can sort of draw parallel between electric field and electric potential. What we are interacting with is the electric potential right now. So you can bring in the V. Okay, we are going to take V, electric potential, to replace the electric field. There will be a charge that is interacting with the electric field. So I'm going to keep the charge Q but without a modulus because I am going to sub in the sign. Okay, so what's the response? In electric field, the response is the electric force. In electric potential, the response is the possession of this electric potential energy. So we're going to put in U over here. Okay, so this is the equation over here. Just I need to again make some statement by saying that this Q over here is the Q charge that interacts with the electric field. Okay, electric potential. Okay, this is a charge that is interacting with the electric potential. In this case, we are going to put Q2. If you are studying position X, Q2 is interacting at position X, and the electric potential energy we're going to bring in this equation and put it. And the V will be the electric potential at this position X. Okay, so if you want to write down the label for the particular situation at X, we are going to say this is the electric potential at X and it's produced by Q1. Okay, so who is producing the electric, who is interacting with, who is the charge interacting at X? That will be Q2. So we're going to put Q2, and the result is the possession of the electric potential energy between Q1 and Q2. So this one is U12. Okay, this is the way of writing it, but I'm going to keep it general, so I'm going to wipe it off. Okay, again, I just want to mention that sign convention change from year by year. Different lecturers, they come together, they'll discuss, and they think this one is more appropriate, that one is more appropriate. For me, as long as you are clear, then it's fine. Okay, so I'm stating it clearly. I'm going to use at where by what, and on what by what. Okay, the by sheet at the back. You review my video from previous years, I might switch my order because it changed from year to year. Okay, so I'll state it usually in my video. Okay, again for direction, for interaction, there's no direction because it's a possession of electric potential energy. Electric potential energy is also a scalar quantity. Energy has no direction. So we're not going to talk about direction over here. Okay, so I hope you can see some kind of parallelism between electric field and electric potential. It's some kind of medium, so that two charges that are not touching each other, they are able to interact with each other. In the electric field and electric force, the kind of interaction is the repulsion or attraction between charges. If it's electric potential, the kind of interaction is the possession of electric potential energy in between them. Okay, so before we end this particular slide, okay, I'm actually done with this slide already. I just want to say that these two equations are actually very much related. Okay, so here I'm going to write a little bit of addendum. So if I bring in, if I'm being specific over here, like what I mentioned just now, this is V at position X produced by 1. This is Q2 that is interacting, and the position of potential energy between 1 and 2, right? So if I choose to expand the equation, I'll get K Q1 Q2 over R, and I'm going to divide it by Q2 as well. So I'm going to put Q2 down here. Okay, K Q1 Q2 over R is the U which I have substituted in, and divide by Q2. And you can see that Q2 and Q2 can cancel. So at the end, you get back the equation that is K Q1 over R. Okay, so you can see you start out with the interacting equation, but if you substitute the equation for this, you can get the produced equation. Okay, just to say that these two equations are actually very much related to each other. Okay, before I end, I would like to tell you that of course, besides analyzing a situation at X, I can analyze a situation at Y as well. Okay, actually forgot about it. If I analyze the situation at Y, then the electric potential at Y will be produced by another charge. So who is producing the electric potential at Y? Q2 will be producing the electric potential at Y. Okay, then who will be interacting with the electric potential at Y? It will be who is standing at Y. Q1 is standing at Y, therefore Q1 will be interacting with the electric potential at Y produced by Q2. So Q1 will be interacting, and because Q1 interacts with the electric potential, Q1 will respond by possessing an electric potential energy, and that electric potential energy is shared with the producer of the electric potential, which is Q2. So Q1, Q2, in between them, there will be this electric potential energy. Okay, so is there anything that I missed out? Okay, maybe I can add on something as well. This equation only valid for point charges. Okay. You can only use this equation if it involves point charges. What is point charges? Basically, charges that has a shape of a point. Okay, if you talk about a parallel plate, or if you talk about a uniform electric field, all those kind of things, you cannot use this equation anymore. Your charge must be in the shape of a point, like this. Point. These are point charges. If your charge shape like this, only you are able to use this equation. Same over here. Only if your charge has the shape of a point, then therefore only then you are able to use this equation. Okay, so only valid for point charges. Why is it so? It depends on derivation. The derivation of all of this comes from Coulomb's law, K(q)(q) over r squared. So K(q)(q) over r squared, Coulomb's law, is in between two charges. So that's why everything that's derived from K(q)(q) over r squared will only can be applied for point charges. So this one only can be used if you're talking about point charges. If you're talking about parallel plate or uniform electric field or those kind of thing, you're not able to use this equation. This equation not allowed to be used for situations that are not point charges. Okay, but this equation can be used everywhere. This equation is general. So let me write it down. This equation is general. Okay, you can use it anywhere. No matter it's point charge or not point charge, you can use this equation. Our space, I'll write it up here. This one is general. Okay, you can use it any situation, no matter it's point charge or not point charge. Okay, so that's it. That's the purpose of this video, is to draw parallel between electric potential to something that you have just learned from the previous section, which is electric field.